right, thanks. Okay, so before we start, I was asked a question via email by one of you regarding what happens if the reference frames we're dealing with don't have the same origin. We are not going to see it today. We'll start seeing it with examples. But remember what we said about the transport theorem is that the rate of change of a generic vector B in a reference frame A is equal to the rate of change ddt in B of the same vector B plus omega BA cross with B. I made no assumptions regarding the vector B. I made no particular assumptions regarding the frames A and B, other than saying that I can write B in a coordinate system fixed to reference frame B, capital B. That's all I've said. So this doesn't change. The transport theorem remains the same, regardless of the frames having the same origin or not. Now, a different story is when in kinematics we start dealing with frames that have different origins, and so the position vector can be expressed as the, and again, we're not going to do it today, but I just want to give you a heads up here. Say that this is your first reference coordinate system attached to the reference frame A, and then your other coordinate system is somewhere else here, and it's fixed in a reference frame B, and you're looking at a particle P. Well, then in this case, we have the position of P as, let's say that this is the origin O, this is Q. You don't need to take notes about this. I'm just opening a brief parenthesis here. So this will be the position of Q, the origin of the other coordinate system. And so in these cases, and this is the position of P with respect to Q, we expressed Rp as the addition of two vectors. So now you are bringing in more vectors to the table. That's why when you start taking derivatives, such as the velocity in A or the acceleration in A, this other point comes to play. But the transport theorem doesn't change at all. We'll see it. There is really no modification to that theorem. The only addition that you will see is that on the table you'll start seeing the velocity of Q and the acceleration of Q as well when you do take your rates of change. But again, there is no assumption regarding the frames here. And I'm sure that in any other classes you may have taken about dynamics, when you started dealing with reference frames that translate and rotate with respect to each other, you started talking about, what are they called? Centripetal acceleration, Coriolis acceleration, all those nice expressions, which if you want, we can derive the huge formula, which I don't recommend you use. I've used it in the past, and that leads to a lot of confusion because you have that formula there and you have to figure out all those terms. You just have to plug in vectors, and that's not really what we're doing in this class. We're focusing on understanding. There is no need for you to use or memorize that formula. We can derive it, but there is a simpler way to actually deal with rotating and translating frames that doesn't require you to memorize Coriolis accelerations and centripetal accelerations and all those nice expressions. Okay, so I just wanted to quickly reply to that question. Again, we'll see it. What we are going to see today is a couple of different coordinate systems that are commonly used. Cylindrical and spherical coordinate systems. Why do we bother about using coordinate systems that are different from Cartesian ones, from x, y, z? And this question came up in one of the past lectures. Well, because in many cases, the geometry of the problem we're looking at lends itself to the use of coordinate systems that are different from the Cartesian ones. It just makes our life easier. This reference frame on which we're living, planet Earth, is more or less a sphere. And things that move with respect to us, airplanes, satellites, they usually, well, they can go in straight lines, of course, but most of the time they will look at them in the sky if I'm looking at an airplane or a satellite. And it's easier for me to say, if I have something to measure, that's the distance from me, and it's going north-south. That's what you do. You don't say that object is x, y, z, whatever, x dot, y dot, z dot. That's extremely difficult. It doesn't it doesn't make sense. You're moving on a sphere, and things move around this sphere. So it is naturally making a little more sense to use spherical coordinates, for example. So that's what you would do when you're looking at a reference frame, which is a sphere or a cylinder. So we'll do both. And this is not just to obtain lengthy formulas that give me velocity and acceleration in those types of coordinate systems. This is also a very good exercise to apply the transport theorem. And in one case, we'll do it also with two rotations. Well, rotations, two angles. So an angular velocity that is composed by two rotations. And I don't know how many of you have tried to attack the problem I gave you. Again, I'm not going to solve problems here. You have plenty of problems on your book. Come to office hours. Start coming to office hours now. Don't wait until the last minute. So if I give you problems or you have a problem from the book, you come and can see how I solve it, or you show me how you solve it. We can talk about the problem. That's what office hours are for. So don't waste those hours that we have every week. Use them. That's my advice. OK, so let me start from actually, and this is going to be to become a pretty busy picture here. I don't want to make mistakes. Let's start from a Cartesian coordinate system. And I'm already skipping steps. And I want you to pay attention if I skip steps here and tell me. I'm starting from a coordinate system. I should have started from a reference frame. So say that there exists a reference frame. Maybe it's this board on which I already picked my 3 points. There I have mutual distances that don't change in time. And I picked an origin which I call O. OK, so I have done that. So this is point O, which is fixed in A. And so this frame here is also fixed in A. This coordinate system is fixed in A. EX, let's call this EX, EY, and EZ. And we're still doing single particles for now. So I'm looking at this particle P in space, and I want to derive its velocity and acceleration. And we'll start doing it. Probably I should put a little, I don't need the title anymore. I can leave it there. OK, so since I already have a coordinate system, I can define the position of P with respect to O, and I'll call it R. Well, if I have a Cartesian coordinate system, well, that's what we're used to doing. We know exactly what the vector R, how it is represented in these coordinate system. So let's call Q this projection of P on the plane EX, EY. We know that this is Z, this distance. Then we have these other two. They're going to be, what is this one? This is Y, right? And this is Z. I'm sorry, this is X. Well, if I'm asking you the position of P with respect to O, and I'll just write it once. We have only one particle. We have only one origin. There is really no point for me to keep dragging this P with respect to O all over the place. But that's what I'm going to assume, that R is R with respect to, of P with respect to O. Well, in that coordinate system, that's pretty simple, right? Nothing special. So if I'm asking you, so my goal here throughout the lecture will be computing the velocity and the acceleration of P as seen by an observer fixed in A. A is where I'm sitting. It's the Earth, if you like. And I'm going to represent, that's what we really do here. I'm going to represent velocity and acceleration of P with different types of coordinate systems. This is one representation. This is one possible representation, which again, if you imagine the reference frame being the Earth, I don't want to mess up this picture, but imagine this being the center of the Earth and EX, EY, and EZ going with the planet. I never seen anyone using X, Y, Z on the planet to talk about the position of velocity or acceleration of a point, of a spacecraft, or whatever it is that you're looking at. That's not what we do. GPS coordinates don't come as X, Y, Z on your cell phone at this point. OK, so d dt of r in A is what I want to compute, and I should have actually, let me do it this way. Okay, this is what I want. I want V in A of P, of course. And so what is this? This is d dt of r in A, well, x dot ex plus y dot ey plus z dot ez. Why? Why is that true? Why can I do that? Ex, ey is fixed in A. Now, this is simple when you look at this, but when things get complicated, you have multiple frames involved. You have to remind yourself in which reference frame each coordinate system is fixed. Otherwise, you make huge mistakes. And likewise, in A, acceleration of P, I'm going to drop this P from everywhere. Bless you. In A is the rate of change, ddt in A of V in A. And that's quite simple, right? X double dot ex plus y double dot ey plus z double dot ez. Nothing special. We know how to do this. Say that now I'm going to, yeah, it's better if I put it down here. I'm going to define a different coordinate system. And you tell me what I'm going to miss here. I'm going to draw a few things. Call that distance O to the projection of P on the plane xy, call it r. This is not a vector, it's just a length of that, if you want the magnitude of OQ. Okay, this, I called it theta. This angle theta. And I'm going to give you this unit vector ER. Is this big enough? Can you see okay? Looks okay on the video. Okay, ER, and then I'm going to use EZ, so I'm not going to change that. And then EZ crossed with ER is going to give me this direction that I call E theta. What did I skip here in doing this? And probably I should tell you a little more about these unit vectors here. Okay, ER is the vector OQ over its magnitude. EZ is given, so E theta is EZ cross with ER. What did I skip here? What did I not do that I was supposed to do? It's simple. I didn't define a reference frame. See, this comes natural. You just start defining vectors, unit vectors, and you skip steps. And that's not good. What is this reference frame that I implicitly assumed I was using? Well, it could be, for example, this plane containing the vector R and the vector OQ. That's a reference frame. It's a plane. You can pick as many points as you want in that plane that have constant mutual distances. So if you want, it's this board that you just start rotating about the z-axis. So that I should have done first. And then I should have told you the origin is the same. O is fixed in A. And now ER, E theta, E z are fixed in B. Let's call this other reference frame B. Let me be specific here. ER, E theta, EZ, it's fixed in B. Okay, I want the same things. I want the velocity of P in A, which is still the same rate of change, d dt of R in A. You can start helping me here. You should. What do we do? If I use that coordinate system.
Define the position of P in the new coordinate system.
Okay, so if I use this coordinate system, what is R? In this new coordinate system, what is it?
RER plus ZZ.
RER plus ZEZ. Okay, that's fine, it's there, I like it. Remember, these vectors are all the same. R is not different from the other one I've defined before. It's just using a different coordinate system. It's just expressed in a different basis. Okay, so what do you suggest I do here? Well, I guess the transport theorem would help, right? D dt of R in B plus omega BA cross with R. At some point, you will have used these so much that you will just have nightmares about this formula. That's what you should get.
Shouldn't that be opposite? B and A? B in reference frame B.
First question first. What is the opposite?
A should be B. B where dt in the form of A we have to write, right?
Okay, I want the velocity. This is what I want. I want the velocity of the point P, I drop notation P, as seen by still the observer fixed in A. This is dr dt of a position with respect to A. Transport theorem tells me that I can add together what the observer fixed in B sees as the rate of change of R plus the cross product of the angular velocity of B as seen by an observer in A with R itself. So that is correct. And then the second question was, why am I not using R in B? Well, the operation of taking the rate of change depends on the frame. The vectors do not depend on frames. So yeah, here I will use dr expressed according to this coordinate system because it makes sense, but that's just a representation of R, right? So the superscript indicating the reference frame definitely goes with velocities and accelerations. You have to tell me who is the observer who computed those rates of change because those do affect the final result, the vector that you get. But not the position vector. Position vector is just a vector. It does change if you change your origin, of course, but you don't need to tell me that it's R in B. And so let's do this. What is this? Well, let's do it one by one. dr dt in B, if I use this expression, is R dot ER plus Z dot EZ. Do we agree with that? Omega of B in A, what is the angular velocity of the reference frame B as seen by an observer in A? Theta dot EZ. Remember, we demonstrated this the moment we ended up demonstrating the transport theorem that for a single axis rotation, that's what you get. And you can prove it to yourself by just playing with coordinate systems. This is an angular velocity between two reference frames. It has nothing to do with the coordinate systems you picked. If one reference frame is it's the board, and the other reference frame, is there a question?
I was confused. It was ED or EZ?
Oh, this?
Up top you define as ET, right? Or I mean, you say, where you define E theta, you say ET cross ER?
Yeah, I think that's.
I'm sorry, that's a Z. That's my writing. Thank you. Good. Easy, yeah. So one of the unit vectors of this new coordinate system corresponds to one of the unit vectors of the original one. That's always the case when you have a single rotation, single axis rotation and common origin. We always pick, as a rule of thumb, one common axis. Okay, the point I was making is this doesn't really depend on which coordinate systems you picked. You can take this EX, EY, Z and just tilt it a little bit, and you will still get the same angular velocity vector. So in this case, the angular velocity is a vector that points in this direction, right? This is omega BA. That's a vector. That's what it is. if you again take these EX, EY, Z and just tilt it a little bit, maybe rotate it about EX 30 degrees, let's say 30 degrees. But the motion between the two reference frames is the same. Doesn't change that vector omega. Remember, the coordinate systems are just lines that you draw on an object, if you like. That's exactly what I'm doing here on the board. But the motion between the objects, the rigid bodies that are reference frames, does not change. Okay? All right, so this allows me to compute this last term here. Omega BA cross with R is going to be theta dot EZ cross with R, which is R ER plus Z EZ. And this is my order of the vectors. And so this will be equal to theta dot R. EZ cross with ER is E theta plus, probably this is a minus, I guess. EZ, well, that's gone. Did I make a mistake? No, that's gone. Okay, that's it. That's all I have. EZ cross with ER and EZ cross with EZ is obviously 0. And I'll try to fix my way of writing Z's. Okay, that's pretty simple. So when I put it all together, the velocity of P in A, let's try to organize it in the sequence R theta Z is R dot ER plus R theta dot E theta plus Z dot EZ. Okay. And as we said, we stop, we look at what we get, and make some comments. These, to me, makes a lot of sense geometrically, probably more than x, y, z, x dot, y dot, z dot, because say that theta, for example, is not changing. It's a fixed angle. All it can happen is that P is moving in a plane, which is contained by the vector R and which is contained in the vector R and OQ. Do we agree with that? If theta is fixed, P is moving in a plane. So this goes to 0. We don't have a theta, E theta component, which makes sense. P will never leave that plane. It can only have an EZ and ER component in the velocity vector, right? The other thing that can happen is, for example, R is not changing. If R is not changing, then definitely there is no ER component. This is making sense. So these are cylindrical coordinates, by the way, that I'm dealing with here already at the end. They already give me a way to visualize motion, which makes some sense. But I'm not done. I want to compute the acceleration, right, as well. Let's see what I need here. I need this, and probably the angular velocity. Now, how would you prove if I asked you to prove that this is the same vector that I computed at the very beginning? How would you do that?
But we are assuming that R is not changing. Is R changing or not?
No, it is. I'm just looking at the final result, and I'm trying to see if it makes sense. I'm just trying to analyze my final result and see if it makes sense. The things that I recommend you do is, if there is geometrical insight, try to get it as an exercise, and also to double check that what you obtain makes sense. It makes sense to me, again, that if there is if I lock theta in place, let's say that for some reason theta is locked, it's not changing, so theta dot is 0. This term goes away. The velocity vector only has a component on the z direction and the r direction, which is making sense. It is constrained to the plane. Another case could be that r is not changing, so p is basically moving on a sphere around the point O. So you will never see a component of the velocity in the ER direction, right? In this direction. Oh, I'm sorry. I'm confusing it with spherical coordinates. With spherical coordinates, R will be the actual distance of P. R here is just a projection. So these are cylindrical, so it still makes sense. If little r, which is the OQ distance here is not changing, then P is moving on a cylinder. At the most, is moving on a cylinder around the vertical axis. And I see that. There is no way that you get a component of the velocity outside of, along ER. It's not leaving that cylinder. It's constrained to, at the most, moving a cylinder around the vertical axis. That was a good question. Yes. Yeah, this is not the actual. So I'll actually call the magnitude of OP, I will call it rho, and we'll do it with spherical coordinates. So in that case, if rho is not changing, P is moving on. It can move on a sphere, for example. Okay, so that's the first thing that I invite you to do. Try to see if you can get, especially with velocities, you can get that feeling for making sense geometrically. Not as much with accelerations, but definitely with velocities. And another good check is, we always forget about this as engineers, but we should do it every time. Dimensions. At some point when we started studying engineering, someone told us that dimensional checks are a good habit, and we have to do it. Do all the terms have dimensions of, say, meters per second, if I'm measuring time in seconds and distances in meters? Well, this does. This was a distance. Z was measured in meters, so this is meters per second. This is also a distance, meters per second. Well, this is radians over seconds, so this is the same. So dimensionally speaking, it also makes sense. If you get a result where this is the velocity and this is a theta double dot, something is not right. You're mixing different things, right? So those are good checks. Okay, let's move on acceleration. A in A is what? Rewrite it every single time. It's d dt in A of v in A, which is also equal to transport theorem, d dt in B of the same vector v in A plus omega b A cross with v in A. Okay. Well, let's do it. First term. Start noticing that when I use the transport theorem and I go from a frame B to A, I usually express things in that reference frame I'm starting from, and then I'm going to A, right? So here I start from B. All these vectors that I obtain the velocity acceleration will be expressed in a coordinate system which is fixed in the reference frame from which I'm starting from B, and I'm going to A. And it makes sense. Now that I want to compute the rate of change of VA in B, well, guess what? The VA is expressed in a coordinate system fixed in B. So this will be pretty easy. You don't have to take the rate of change of ER, E theta, and EZ. That will be always the case. So there's a sequence here, right? There's a procedure that we follow that helps us obtaining the rate of change of whatever it is that we're computing in the final reference frame in A. Okay, so this d dt of VA in B is, again, I just take the rates of change of the components here, R double dot ER plus R dot theta dot plus R theta double dot E theta plus Z double dot EZ. That's the first one. Omega BA is the same, so I can just go and try to do that, compute that cross product. Omega BA cross with V in A is theta dot EZ, right? Cross with R dot ER plus R theta dot E theta plus Z dot EZ. Okay. And once again, I don't care what you think about me doing this all the time, but I don't want to make mistakes. So I remind myself this was the sequence, and I look at that, and I do it. EZ with cross with ER is E theta, so the first term is going to give me R dot theta dot EZ, E theta. The mistake here? No. So first vector of the coordinate system is ER, the second is theta, the third is Z. So if I have EZ cross with ER, which seems like that's what I have, it's E theta, right? Okay, plus EZ cross with E theta. Now that's a minus, so let me just put the minus here. Minus R theta dot squared. This is bookkeeping. This is doing algebra now. I'm assuming that all of you can do this. You need to be careful. So my way of being careful is just drawing this all the time and checking. I can still make mistakes. And if you make mistakes at this point, it's not as big of a deal if you don't apply the transport theorem right. This is just bookkeeping of cross products. Where was I? This is a minus ER, right? And then that's all I have. So let's put it all together here. The acceleration of the point P as seen by an observer in A is all that plus the second line. Let's see if I can put it all together without missing any pieces. R double dot minus R theta dot squared ER, and that takes care of these two terms here. Then I have, see, I have two, okay, I have R double dot plus 2 R dot theta dot E theta plus Z double dot EZ. That's it. Do I want you to memorize these? Absolutely not. I will never memorize these. You have to be able to get to this point by yourself. And the transport theorem is really the only starting point. Following the sequence, defining reference frames, coordinate systems, understanding what the angular velocity is, and then use the transport theorem is all you have to do. This is bookkeeping. This is you can do it. So memorizing these has no point. Same way as memorizing the Coriolis acceleration and all those other terms in those formulas that we've been given for years, it doesn't make much sense. You don't need to. Very little memory in this class. Just a few concepts. Okay, these are cylindrical coordinates, and again, I don't want to go through the exercise of trying to visualize these because I have a hard time visualizing accelerations. I can probably visualize velocities, but accelerations are rates of change of velocities, so it's not as simple. But you can still do the check in terms of dimensions if all these are meters over second squared, for example. And again, if you want to convince yourself that VA is the same expressed in this coordinate system or in the original one, I invite you to do it. How would you do this? They must be the same vector, because that's a vector. It doesn't care. The vector doesn't care about your reference frame or coordinate system. It's a vector. It does exist in 3D Euclidean space, so it doesn't matter if you write it like this or like this. It needs to be the same. So if you want, you can go through the exercise of, for example, projecting ER, E theta, and EZ in these other bases, substitute, and prove to yourself that they are exactly the same vector. You can. I'm not asking you to. And as we will address more complicated problems, as long as we are in kinematics, I don't really care which coordinate system you're giving me the result in, as long as it makes your life easier. You can even mix coordinate systems to give me the final answer. I don't care. After all, they're all vectors. So you can give me an answer that looks like, I'm just making this up. A of A equal to R theta double dot ER plus Z double dot big EZ. That has to do with a completely different coordinate system. You can. You don't go through the pain of transforming these in the other coordinate system unless I ask you to do so. When we do kinetics and we start dealing with forces, then there is no choice. You have to write everything in the same coordinate system. Otherwise, things don't show up as they should. But in kinematics, no, you're done. You get velocity, acceleration, you stop there. It doesn't matter if it's the same coordinate system you're using. Okay? So these are cylindrical coordinates. If there are no questions, we'll move on and add yet another coordinate system to this drawing here. Okay. Okay, let's see what I called it here. I don't want to be inconsistent. Okay, yeah, I called this distance rho, and then I'll define UR. Let me see what I've done. Okay, UR is along the R vector. So it's a unit vector along the vector OP. So UR is OP over its magnitude. Let me draw the coordinate system up here, but again, the origin is still O. Remember, I can move the basis vectors wherever I want, whatever makes it easier for me to draw them. It doesn't, they're free vectors. I'm going to use the same E theta, so the U theta, this is kind of hard to draw, but it's parallel to E theta down there. So they have a common vector. And then U phi is going to be pointing down this way. And this angle, let's call it phi. Okay? And what have I skipped again? Reference frame. Reference frame. Which one should I define here? Yeah, what would you choose? There's probably another plane here that makes sense, right? What would you do?
Rotation along E theta.
So we said before the reference frame was this plane, for example, right? What can you choose as an object in 3D Euclidean space, a plane, another plane, I guess, that makes sense here, such that this coordinate system is fixed in that reference frame. And let's call that C, right?
Plane defined by OPQ.
That was what I used before, right? Yeah, you could. You could use the same plane and allow it to rotate of an angle phi, right? I mean, you don't have to tell me every single time. You have to, it's a good idea to go through the exercise of saying that if there is a new coordinate system, there is also a new reference frame. So in other words, really the difference between the reference frame B and the reference frame C is that C is rotating about E theta of an angle phi. That's really what it is. Does it make sense? If we don't see it, let me finish this definition here, and then we'll comment on that. So U phi is going to be the cross product of these two is U theta cross with U r. So basically, my vectors are defined according to this order here. U theta. This is the order of definition of my vectors. To see how things are moving with respect to each other, since doing it in 3D, it's kind of complicated. We do it in 2 dimensions. In 2 dimensions, I can put myself in this plane, OPQ, and see that if this is EZ, and this is ER here, then I see U phi pointing down here, and the UR being this vector up here. Right? Making sense? Yes? No? Maybe? You don't care? Yes?
How exactly do we fix that U phi is U theta cross U r? I mean, why couldn't be like U theta equals U phi cross U r? I don't understand how the order.
Well, I'm just building. So when I introduce a new coordinate system, a new reference frame, and then a new coordinate system, that basically means that there is a new rotation. The rule of thumb is if there is a single axis rotation, there are definitely two reference frames that are moving with respect to each other, of course. Each new rotation is a new reference frame, right? And so this rotation that I've defined, it's clearly about E theta. So why would I bother changing that E theta? So as before I've reused the EZ direction, which was the direction of the rotation, I'm reusing the U theta direction, which is the direction of the rotation, right? So it is usually the case when you introduce a new reference frame, it means that there is a new rotation and one axis will be in common with the previous one. Yeah, by doing all these problems, it will be making more and more sense that there are these repeated offenders, if you like, that are the same in two coordinate systems. So that's why I went ahead and defined this UR, then I reused E theta, and then complete the right-handed frame that way. The only thing is that I decided my second one is U phi rather than U theta, but I can do that, right? And so in 2D, I do see that there is a single axis rotation here, and definitely the two reference frames are basically the same. They just rotated of an angle phi. Okay. Well, I want to do the same here, right? Velocity and acceleration of p as seen by an observer fixed in A. These are spherical coordinates now. Before we did cylindrical, these are spherical coordinates. And we will see, especially in the velocity, that when the r does not change, I was confusing it before, you get a motion on a sphere. Just to be thorough here, let me actually draw another picture. OK, I don't think we need this anymore. These coordinates, theta, phi, and r, and rho, are what we use on our GPS. So the goal, what we've done before, we obtained velocity and acceleration, and that was a function of the coordinates that I've defined, which were theta, r, and z. So what I expect to obtain now is the same velocity and acceleration. Again, it will be the same vector, but now my coordinates are theta, phi, and rho. Okay? And those are really what you use. This would be hard to draw on the planet. So if this is planet Earth, and say this is one direction from which you start counting longitude, and you have a point here that you're looking at, and this is its position in space with respect to the center of the planet, and then you project the point down here, exactly what we've done there. Well, this angle is what we call what? What do we call that angle? That's the longitude. This is actually the latitude, and then there is distance from the center of the Earth, or from where you are on the surface, if you like. Since the radius of the Earth is assumed to be constant, even though it's not true. It's not even a sphere, but we assume that. So here I'm using, so this theta is longitude, ni is latitude, and so the angle that I'm actually using there, it's co-latitude. And it's usually done that way because using co-latitude makes things a little easier in the final expressions. But since we don't really like measuring things from the North Pole, we just go from the equator, and we use latitude. So rho is distance, right? Rho is height, if you want. Okay. Just to give you an idea of what it is that we're doing, we're trying to express velocity and acceleration of this satellite, airplane, whatever it is, in using parameters, rho, ni, and rho, that are commonly used, that we use every day. Okay. What is r in this new coordinate system? That's it. We'll finish it next time. Wasn't going to take just one lecture. Okay, so I want v of p in A. This is the same every time, d dt in R as computed by an observer in A. Now this is going to be, remember I am in reference frame C now that I'm working from. So this is d dt in R, d dt of R in C plus omega CA cross with R. Now we have a problem here. We have to find these. There are two rotations now with respect to A. There is theta and phi. Well, but I know that this is, we demonstrated this is omega BA plus omega CB. Do we agree? Remember what we said last time? I'm going from C to A. So I'm going first from C to B and then from B to A. And this, I know it already. I've done it before. This is theta dot EZ. Now what is this? Phi dot U theta. Right? And so omega of C in A is going to be theta dot EZ plus phi dot U theta. Now, if my question was find this angular velocity, you would be done here. This was the question for this problem. You would be done. I don't care that EZ and U theta are two unit vectors belonging to bases in different coordinate systems. I don't care. These are two vectors. This is a vector. This is a vector. I can add vectors. If I don't need to go beyond this point, you're done. This is fine. Unfortunately, I will have to do this cross product here, and probably things are not as fine to go ahead and use this because it will give me a very hard time when I do the cross product. So in this case, I definitely have to be consistent and use one coordinate system only in my calculations. Which one do you think I should use? Remember what we said before. We start from a coordinate system, from a reference frame, where I can measure things, where I can express the vector, and I want to go to another one. So I use the coordinate system attached to the reference frame from which I am starting. I start from C. I am in C, and I want to go to A. So I have to express this little AZ in UR, U theta, U phi before I can proceed and do that cross product. Well, how do you do it? Forget doing things in 3D. I don't want you to do things in 3D unless you're really that great, but do it in 2D. So this is your EZ here. We've done it before. I have to redraw it. This is your ER, and then you will have yes, UR, U phi, right? Make sense? So what is it that I'm trying to do here? I'm trying to express EZ in these other bases. What is EZ? What is EZ? UR cosine of theta, so cosine of phi, I'm sorry, cosine of phi UR plus, is that a plus? Minus sine of phi, what do I have? U phi. Making sense? Oops. And so, okay, my omega CA is theta dot cosine of phi UR plus, don't want to forget this term. Remind me that I have an extra term here. So theta dot cosine UR minus sine of phi U phi. Okay, that takes care of the first one, plus phi dot U theta. Okay, now I can proceed. Now everything is in the coordinate system fixed in C. Finish next time, of course. Next time is Wednesday, by the way. Class on Monday, right? Yes?
Can't we use like Ez is a cross
Product of ER and E theta. We have E theta, U theta, and we can easily use ER in the reference frame. And
oh yeah, you can do, I mean, if you can do this cross product by skipping this step, you're more than welcome to do it. You will, but you have to do it right so that you see these sines and cosines coming up. Yeah, I mean, the cross product is also defined as, you know, the magnitude of the two vectors, in which in this case is 1, and there is the angle involved, the sign of the angle, right? So you can do it that way. I never do it that way because I tend to make mistakes. But yes, of course you can. EZ cross with UR, you can do it. You can do it directly and tell me that is U theta, that's what we'll get. I just don't like skipping steps because that's usually where you make mistakes. Okay, so we'll finish this time. You're more than welcome to continue, substituting here, and then start doing the acceleration, which we'll do next time. We'll get it.